There is no such thing as nothing. Not here, not anywhere in this universe. Even the deepest, darkest, most remote corner of space, stripped of every atom, every photon, every trace of matter, is still quietly alive with something. Welcome to the Sleepy Lab. Tonight, you will drift through the strange and subtle world of the quantum vacuum, through the hidden energy that fills empty space, the invisible fluctuations that shape the very particles you are made of, and the quiet restlessness that lies beneath everything. If any of this settles gently into your nights, consider subscribing, one sleepy soul at a time. Now, let's begin. Picture the emptiest place you can imagine. A vast region of space, far from any star, far from any galaxy. No light, no dust, no sound, nothing moving, nothing present. And yet, even there, the universe is not at rest. Quantum field theory, the framework physicists use to describe the fundamental nature of matter and energy, tells us something quietly remarkable. A perfect vacuum, one containing absolutely nothing at all, is not merely difficult to achieve. It is physically impossible. The universe, at its deepest level, simply does not permit it. To understand why, it helps to think about what the universe is actually made of. Not particles, exactly, not objects sitting in space, but fields, vast, invisible structures that stretch across all of space and time. The electromagnetic field, the electron field, the Higgs field, each one present everywhere, always filling the cosmos like an ocean fills a basin. And every one of these fields has what physicists call a ground state, its lowest possible energy configuration, the state it settles into when nothing is disturbing it, when no particles are present, when everything is, as far as we can tell, quiet. But here's the thing. That ground state energy is not zero. It cannot be. This is not a flaw in the theory. It is not an approximation or an oversight. It is a direct consequence of one of the most fundamental principles in all of physics, the Heisenberg uncertainty principle. The uncertainty principle places a hard limit on what can be precisely known about any physical system at the same time. You may have heard it described in terms of particles, that you cannot know both the position and the momentum of a particle with perfect precision simultaneously. The more precisely you pin down one, the more uncertain the other becomes. But the principle runs deeper than particles. It applies to fields as well. A quantum field cannot simultaneously have a perfectly precise value and a perfectly precise rate of change. If the field were completely still, if it had an exact value and an exact rate of change of zero, that would violate the uncertainty principle. It would be too precisely defined, too perfectly at rest. And so the field fluctuates, not because something is disturbing it, not because energy is being added from outside, but because the mathematics of quantum mechanics requires it. The field must always carry some residual, irreducible energy, a kind of built-in restlessness that cannot be removed no matter how carefully you cool the system, no matter how thoroughly you evacuate the space. This minimum energy is called zero-point energy, and it is present in every quantum field, everywhere, always, even at absolute zero temperature. The coldest state matter can theoretically reach. Even there, the fields do not go still. They cannot. The uncertainty principle will not allow it. It is worth pausing on that for a moment. Absolute zero. The point at which all thermal motion ceases. The point at which, in classical physics, everything would simply stop. And yet, in quantum field theory, even at absolute zero, the vacuum hums, quietly, imperceptibly. but without pause. These fluctuations are not noise added to the theory to make it work. They are not a correction, not a patch, not an artifact of incomplete understanding. They are a fundamental prediction, something the mathematics of quantum field theory produces naturally, necessarily as a direct consequence of its deepest principles. The quantum vacuum, then, is not empty space. It is the lowest energy state the universe can occupy, the quietest it is ever allowed to be, and even that is not a state of rest. Think of it like the surface of a very still lake. Not a frozen lake, not a solid, motionless surface, but a liquid surface, always gently moving, always carrying tiny ripples even when no wind blows and no stone has been thrown. The ripples are not caused by anything external. They arise from the nature of the water itself, from the thermal motion of its molecules, from the subtle interactions between them. The quantum vacuum is something like that. Except the ripples are not thermal. They are not caused by heat or motion or disturbance. They arise from the nature of the fields themselves, from the irreducible uncertainty baked into the fabric of reality. And these ripples have consequences. Real, measurable, experimentally confirmed consequences. The vacuum is not a passive backdrop against which physics happens. It is an active participant, shaping the behavior of particles, influencing the forces between them, and, as we will explore tonight, reaching all the way up to the largest scales of the cosmos. But for now, just rest with the idea itself. The space around you, the air between your fingers, the darkness behind your closed eyes, the vast distances between galaxies, is not empty. It is filled with something that has no name in ordinary language, a kind of structured nothingness, a restless quiet, an energy that cannot be removed, cannot be stilled, cannot be reduced to zero. The universe, it turns out, does not know how to be nothing. And perhaps that is why there is something rather than nothing at all, though that question, gentle and enormous, is one we will leave for another night. For now, let the vacuum be what it is. Not empty, not still, but quietly, endlessly, irreducibly alive. And within that restless quiet, something stranger still is happening. The vacuum does not simply hum with energy in some abstract, undifferentiated way. It flickers. It produces, for the briefest of moments, something that looks almost like matter, and then takes it back. Across the vacuum, pairs of particles are constantly appearing. A particle and its antiparticle, born together out of nothing, existing for an interval so short it barely deserves the word moment, and then annihilating each other, returning to the field from which they came. These are called virtual particles. The name is worth sitting with, not imaginary, not metaphorical, virtual, in the sense that they exist within the mathematics of the theory as genuine, necessary contributions. They are real enough to affect the world, but they cannot be caught, cannot be held up and examined directly. They live and vanish too quickly for any detector to register them as individual events. What we can detect are the marks they leave behind. Think of it this way. A real particle, an electron, say, does not travel through empty space alone. It moves through a vacuum that is constantly producing these brief, flickering pairs around it. Virtual electrons and positrons winking in and out of existence in its vicinity. And each of those fleeting pairs interacts, however slightly, with the real electron passing through. The result is that the electron we measure is not quite the bare, isolated thing the simplest version of the theory would suggest. It is dressed, surrounded by a cloud of virtual activity that subtly shifts its properties, its energy levels, the way it responds to a magnetic field. These shifts are small, but they are not zero, and they are not random. They are precise, calculable, and they match what experiments actually find. This is what it means to say the vacuum has real physical consequences. Not that something dramatic happens, but that the quiet, invisible activity of the vacuum leaves a fingerprint on every particle in the universe. And we can read that fingerprint if we look carefully enough. And there is one place where physicists have looked with extraordinary care. Two metal plates, uncharged, parallel, placed very close together, separated by a gap so narrow it would be invisible to the eye. And between them, in what appears to be a perfect vacuum, something happens. The plates are pushed together, not by any obvious force, not by gravity, not by magnetism, not by any charge on the plates themselves, by the vacuum. This is the Casimir effect. To understand why it happens, it helps to think about what the vacuum actually contains between those plates and what it contains outside them. The vacuum fluctuations we have been describing are not all the same. They come in different wavelengths, different modes, like the different notes a string can vibrate at. And in open space, the vacuum supports all of these modes freely, every wavelength, every frequency humming along in the background of empty space. But when you place two metal plates very close together, you impose a constraint. The gap between them is finite, and only certain wavelengths can fit inside a finite space, specifically those whose wavelengths divide evenly into the gap. Longer wavelengths, those that do not fit, are excluded. Outside the plates, the vacuum remains unrestricted. All modes are present. The full, unfiltered hum of the quantum vacuum, extending in every direction. Inside the gap, the menu is smaller, fewer modes, a quieter, more constrained version of the vacuum. And this difference in pressure, more vacuum activity pushing in from outside, less pushing out from within, creates a net force. The plates are nudged toward each other by the asymmetry of the vacuum itself. It is a gentle force. At the distances where it has been measured, gaps of a few hundred nanometers, a fraction of the width of a human hair, the force is roughly equivalent to the weight of a small water droplet resting on a surface. Not dramatic, but real, measurable, reproducible. The man who first predicted this was a Dutch physicist named Hendrik Casimir. In 1948, Casimir was working on a seemingly unrelated problem, the forces between colloidal particles in solution, when he and a colleague, Dick Polder, began to notice something unexpected in their calculations. The forces they were computing seemed to have a contribution that could not be explained by ordinary electromagnetic interactions alone. Something else was present in the mathematics. Casimir traced it back to the vacuum, to the zero-point fluctuations of the electromagnetic field, and he realized that two conducting surfaces, placed close enough together, would experience a force arising purely from the structure of the vacuum between them. He published his prediction, and then, for nearly 50 years, it remained largely a theoretical curiosity, elegant, intriguing, but difficult to test with sufficient precision. The problem was not that the effect was doubted. The problem was that measuring it accurately required controlling the geometry of the plates with extraordinary care. Any tilt, any roughness in the surface, any contamination, all of it would obscure the signal. The technology to do it cleanly simply did not exist for a long time. Then, in 1997, a physicist named Steve Lamoureux performed the measurement. He used a torsion balance, a delicate instrument that could detect the tiny twist produced by a small force in carefully shaped surfaces in a controlled environment, and what he found matched Casimir's prediction to within about 1%. 1% for a force arising from nothing, from the vacuum, from the difference between the modes of empty space inside a gap and outside it. That agreement is not a coincidence. It is confirmation. The vacuum fluctuations are not a theoretical convenience. They are a physical reality, and they push. There is something quietly profound about the Casimir effect that is worth resting with for a moment. We tend to think of forces as arising from things. Gravity arises from mass. Electromagnetism arises from charge. Even the forces between molecules arise from the distribution of electrons within them. Forces come from something. But the Casimir force arises from the structure of nothing, from the geometry of the vacuum, from the fact that empty space, when constrained, behaves differently than empty space when unconstrained, and that difference has physical consequences. It means that the shape of a region of space matters, that the boundaries you draw around emptiness change what that emptiness does. Two plates floating in a vacuum, with no charge, no current, no material connecting them, and yet the vacuum between them is different from the vacuum outside them, and that difference reaches across the gap and pulls the plates together. The universe, it seems, does not allow even geometry to be neutral. And this is only the beginning of what the vacuum can do. The Casimir effect is one of the cleaner, more tractable demonstrations of vacuum physics, a place where the theory makes a specific, quantitative prediction about a specific, measurable force, and the experiment confirms it. But the vacuum's influence does not stop at metal plates in a laboratory. It reaches into the energy levels of atoms, into the way light is emitted, into the behavior of superconductors and the structure of space-time itself, into questions about why the universe is expanding the way it is, and what the ultimate fate of everything might be. All of that is still ahead. For now, let the image settle. Two small plates, suspended in darkness, in what appears to be nothing, and the nothing itself pressing them together. Quietly, persistently, without pause. The vacuum at work. That 1%, it is worth pausing on. The Casimir force, a force arising from nothing more than the geometry of emptiness, from the way two metal plates reshape the landscape of vacuum fluctuations around them, matches what the equations predict to within about 1%. That is not an approximation. That is not a rough agreement between a tidy theory and a messy world. That is a theory reaching into the structure of the vacuum itself and returning a number that the universe then confirms. 1%. In physics, that kind of agreement is not taken lightly. It means the picture is not merely suggestive. It means something real is being described. And yet, the Casimir effect, precise as it is not the most precise confirmation the vacuum has offered us. For that, we have to look somewhere smaller, somewhere quieter, into the interior of a single hydrogen atom. A hydrogen atom is the simplest atom in existence. One proton, one electron, and between them, a set of energy levels, specific, discrete rungs on a ladder that the electron can occupy. Quantum mechanics describes these levels with great precision. For a long time, physicists believed they understood the hydrogen atom completely. The equations seemed to account for everything. But in 1947, a physicist named Willis Lamb looked more carefully. He found something the equations had not predicted. Two energy levels that the theory said should be identical, that should sit at exactly the same height on that ladder, were not, in fact, identical. One was shifted, very slightly, above the other. The difference was small, extraordinarily small. But it was real, and it was measurable, and it was consistent. This became known as the Lamb shift. And the question it immediately raised was, what is causing it. The electron in a hydrogen atom does not sit still. It occupies a kind of smeared probability cloud around the proton, and as it does, it is immersed in the quantum vacuum. The vacuum fluctuations, those ceaseless, unavoidable oscillations of every quantum field, are present everywhere, including inside the atom. They nudge the electron, constantly, gently, in ways that are too small to see directly, but not too small to measure in the aggregate. These nudges shift the electron's energy levels, not by much, but by a precise, calculable amount, and that amount matches the Lamb shift. The vacuum, in other words, reaches inside the hydrogen atom and rearranges it, slightly, quietly, but measurably. Willis Lamb received a share of the Nobel Prize in Physics in 1955 for this measurement, and what made it so significant was not just the discovery itself, but what it demanded of the theory. The Lamb shift was one of the earliest clear experimental signals that the quantum vacuum is not a passive backdrop. It is not the absence of physics. It is physics, active, present, and precise enough to leave fingerprints inside the simplest atom in the universe. To account for the Lamb shift, and for the Casimir effect, and for a growing list of other phenomena that classical physics could not explain, physicists needed a new framework, a deeper one that could describe not just particles and fields in isolation, but the way they interact with each other and with the vacuum at every scale. That framework is quantum electrodynamics. It is usually called QED. QED is the theory of how light and matter interact. More precisely, it is the theory of how electrons and photons, and the electromagnetic field that connects them, behave when you take quantum mechanics fully seriously. It treats the electromagnetic field not as a smooth classical wave, but as a quantum field, one that has its own ground state, its own zero-point energy, its own fluctuations, even in the absence of any photons. In QED, every interaction between light and matter is mediated by the vacuum. An electron does not simply sit in space. It is constantly interacting with the electromagnetic vacuum around it, absorbing and re-emitting virtual photons, being nudged by fluctuations, having its properties subtly modified by the structure of emptiness. The Lamb shift falls out of QED naturally. So does the Casimir effect. So does a long list of other phenomena, each one a different window onto the same underlying reality, that the vacuum is not nothing, and that any theory which treats it as nothing will eventually fail. But QED does more than explain these effects. It predicts them, quantitatively, precisely in advance, and then the experiments confirm the predictions. The most striking example is a quantity called the anomalous magnetic moment of the electron. The electron behaves like a tiny magnet, and the strength of that magnetism can be measured with extraordinary precision. QED predicts its value, and the agreement between the prediction and the measurement is, as far as anyone can determine, exact to roughly 1 part in a billion. 1 part in a billion. To put that in some kind of scale, if you were measuring the distance from here to the far side of the planet, and your measurement was accurate to 1 part in a billion, you would be accurate to within about a centimeter. That is the level of agreement between QED and the physical world. It is, as far as we know, the most precisely tested theory in the history of science. And at the heart of it, woven into every calculation, every prediction, every confirmation, is the quantum vacuum, the fluctuations, the zero-point energy, the structure of emptiness that the theory insists is there, and that the experiments, again and again, confirm. There is something worth sitting with in that. We began with a philosophical intuition that has been with us for a very long time, the idea that empty space is simply the absence of things. the container in which things happen, neutral, inert, without properties of its own. And what physics has found, slowly and carefully, through measurements of metal plates and hydrogen atoms and the magnetism of electrons, is that this intuition is wrong. The vacuum has structure, it has energy, it fluctuates, it interacts with every particle that passes through it, it shifts energy levels, it generates forces, it shapes the behavior of light and matter at the most fundamental level we have yet been able to probe. And the theory that describes all of this, QED, does so with a precision that has no parallel anywhere else in science. Not approximately, not qualitatively, but to 1 part in a billion. In a universe that did not have to be so orderly, in a vacuum that did not have to be so consistent. The vacuum holds still for the measurement. Every time, there is a kind of quiet reliability in that. The fluctuations are ceaseless, but they are not chaotic in the way that word usually implies. They follow rules, deep rules, rules that were apparently written into the structure of reality before the first atom formed, before the first photon traveled, before any of this existed in the form we now observe. The vacuum was there first, and it has been doing this, fluctuating, nudging, pressing, shifting, ever since. Long before there were atoms to shift, long before there were plates to press together, long before there was anyone to notice. It continues now, in the space between the particles that make up everything around you, in the air that is not quite air, in the darkness behind your closed eyes. The vacuum, quietly at work. And yet the vacuum does more than press. It reaches into the very nature of charge itself. Consider an electron, a single, real electron sitting in space. Around it, the vacuum is not passive. Virtual pairs of electrons and positrons flicker into existence and vanish again, as they always do. But in the presence of a real charge, those pairs do not appear entirely at random. The positrons, carrying opposite charge, are drawn, ever so slightly, toward the electron. The virtual electrons are pushed, ever so slightly, away. This happens continuously, in every direction, at every moment. The effect is called vacuum polarization. The virtual pairs arrange themselves like a soft cloud of screening around the real charge. And because of that screening, the electron's charge appears slightly different depending on how close you are to it. From far away, you see a charge that has been partially masked, softened by the surrounding cloud of virtual pairs. Move closer, and you begin to see past the screen. The charge appears a little stronger, a little more itself. The electron has not changed. The vacuum has simply been rearranging itself around it, as it always does, and the rearrangement has consequences. This is not a small theoretical correction. It is a measurable effect. The way an electron interacts with other particles depends, in a precise and calculable way, on the distance between them, and that dependence is partly a record of the vacuum's constant activity around every charge in the universe. Every charged particle you have ever encountered has been wearing this quiet coat of virtual pairs. Every interaction between charges has been shaped, at least a little, by the vacuum arranging itself in between. The vacuum does not simply exist around matter. It responds to it. And it does something else, too. Something that touches the light you have seen, the warmth you have felt, the color of every flame and every star. When an atom absorbs energy, one of its electrons moves to a higher energy level. It sits there, in that elevated state, holding the energy like a breath held in. In classical physics, the older picture of the world, there is no reason for that atom to ever release the energy on its own. Nothing is pushing it. Nothing is pulling it. It should simply remain excited indefinitely, unless something from outside disturbs it. But atoms do not remain excited indefinitely. They release their energy as photons, as light, and they do so spontaneously, without any apparent external cause. This has always been observed. It has always been measured. But for a long time, the reason was not fully understood. The quantum vacuum provides the answer. The vacuum fluctuations, those ceaseless, gentle oscillations of every quantum field, are always present around the atom. They are not nothing. They carry energy. They nudge. And it is that nudge, that infinitesimal perturbation from the fluctuating vacuum, that tips the excited atom over the edge. The atom does not wait for a signal from outside. The signal is already there, woven into the fabric of the space the atom occupies. The vacuum whispers, and the atom responds, and a photon is born. This process is called spontaneous emission. It is responsible for nearly all the light that has ever existed in the natural world. Every photon released by a cooling star, every photon emitted by a glowing filament, every photon that has ever traveled from a distant galaxy and arrived, after billions of years, at a telescope. All of it initiated by the same quiet mechanism, the vacuum, fluctuating, nudging, releasing. Without the quantum vacuum, an excited atom would hold its energy forever. The universe would be dark in a way that is difficult to fully picture, not merely dim, not merely cold, but silent in the deepest sense. Matter holding energy it could never release, light that could never begin its journey. The vacuum makes light possible, not as a container for light, not as a medium through which light travels, but as the initiating cause, the first, invisible push that sets every photon in motion. There is something worth resting with in that. The light that has ever reached your eyes, every sunrise, every candle, every distant point of light in a night sky, began with a fluctuation in empty space. The vacuum was there at the beginning of every photon, and it is still there now, in the darkness behind your closed eyes, nudging atoms that will release photons you will never see, in a room that is never quite as still as it seems. Let that settle. There is one more thing to hold gently before moving on. A prediction so strange that it sits at the edge of what the mind finds comfortable, and yet it follows, with quiet inevitability, from the same principles. The quantum vacuum looks different depending on how you move through it. For an observer at rest or moving at a constant velocity, the vacuum appears as it has been described here, empty of real particles, filled only with fluctuations, cold in the thermodynamic sense, at absolute zero. But for an observer who is accelerating, not moving at a steady speed, but genuinely accelerating, changing velocity, the vacuum does not look the same. To an accelerating observer, the vacuum appears warm. Not metaphorically, not approximately. Warm in the precise, physical sense, as a thermal bath of real particles, arriving from all directions, carrying energy that a stationary observer in the same location would not detect at all. This is called the Unruh effect. It was described theoretically by William Unruh in 1976, and it remains one of the most quietly unsettling predictions in all of physics. Two observers, occupying the same region of space, at the same moment, one at rest, one accelerating, would give completely different accounts of what the vacuum contains, and both accounts would be correct within their own frames of reference. The vacuum is not a single, fixed thing that all observers agree upon. Its character depends on how you move through it. The temperature an accelerating observer would measure is extraordinarily small for any acceleration achievable in a laboratory, far too small to detect directly with current technology. To feel a vacuum temperature of even 1 degree above absolute zero, an observer would need to accelerate at roughly 10 to the 20 meters per second squared. That is an acceleration so vast, it has no analog in ordinary experience. And yet the mathematics is clear. The effect is real, in the sense that it follows necessarily from the same framework that has been confirmed in every other context. The vacuum that appears empty to one observer appears populated to another, simply because of the difference in their motion. This is not a paradox. Exactly, it is a reminder that the vacuum is not a backdrop painted onto the universe, fixed and universal, and the same for everyone. It is a relational thing, a thing that depends on perspective, a thing that shifts quietly, depending on where you stand and how you move. The same space, the same moment. Two different vacuums. There is no contradiction in that, only a deepening of what the word empty has ever meant. It has never meant nothing. It has never meant still. And now it does not even mean the same thing to every observer. The vacuum holds more than fluctuations. It holds a kind of perspective. And somewhere in that, in the idea that even emptiness is not absolute, that even the ground state of reality looks different depending on how you move through it, there is something that asks to be held quietly, without urgency, without needing to be resolved. The vacuum, patient and various, still fluctuating, still nudging, still, in its own way, alive. And yet, both descriptions are true. The observer who accelerates through the vacuum and feels warmth, and the observer who remains still and feels nothing. They are not disagreeing about reality. They are each describing it correctly, from where they stand. This is one of the quieter revelations in modern physics, that two accounts of the same region of space can differ completely, and neither one is wrong. The vacuum does not have a single face. It presents differently, depending on the motion of the one who looks. And if that feels strange, it may help to hold it loosely, not as a problem to be solved tonight, but as a shape to rest beside. There is a place in the universe where something similar happens, but more dramatically, and with consequences that last for an almost unimaginable span of time. Near the edge of a black hole, at the boundary called the event horizon, the vacuum does something that nowhere else in ordinary space quite manages. Vacuum fluctuations happen everywhere, as they always do. A virtual particle and its antiparticle appear together, exist briefly, and then find each other and annihilate. This is the ordinary rhythm of empty space, playing out across every cubic centimeter of the universe, always. But near the event horizon, the geometry of space is so severely curved that this ordinary rhythm can be interrupted. A pair appears, as pairs always do, but the horizon falls between them. One particle finds itself just inside the boundary, pulled inward, unable to return. The other finds itself just outside, and with nothing to annihilate against, it has no choice but to become real. It escapes. It drifts outward, away from the black hole, carrying energy with it. And that energy had to come from somewhere. It came from the black hole itself. This is Hawking radiation, named for Stephen Hawking, who described it theoretically in 1974. It is the process by which black holes, over time, slowly lose mass. Not quickly, not in any way that could be observed directly with current instruments, but steadily, in the only way the vacuum knows how to work, through fluctuation, through the quiet splitting of pairs that were never meant to be separated. The timescales involved are almost beyond holding in the mind. A black hole of stellar mass, the kind left behind when a large star collapses, would take something on the order of 10 to the 67th years to evaporate completely through Hawking radiation. The current age of the universe is roughly 14 billion years, which is 10 to the 10th. So the evaporation timescale is not just longer than the age of the universe, it is longer by a factor that itself requires scientific notation to write. And yet the process is real, as far as we can tell. The vacuum, patient beyond any ordinary sense of patience, slowly, gently, draining the most massive objects in the cosmos. There is something in that worth sitting with for a moment. The same fluctuations that nudge an excited atom into releasing a photon, the same fluctuations that press two metal plates together across a gap of nanometers. Those same fluctuations, operating near the curved edge of a black hole, are enough, given enough time, to unmake it entirely. The vacuum does not hurry. It does not need to. And then there is the question of what the vacuum weighs. This is not a poetic question. It is a precise one, with a precise and deeply puzzling answer. Einstein, in his equations describing the large-scale structure of the universe, included a term called the cosmological constant. He introduced it for reasons that turned out to be mistaken, and later set it aside, but the term itself never quite went away. In the framework of quantum field theory, the cosmological constant has a natural interpretation. It is a measure of the energy density of the vacuum, the amount of energy contained in each cubic meter of empty space, simply by virtue of being the quantum vacuum. And quantum field theory makes a prediction about what that energy density should be. The prediction is very large. Depending on how the calculation is approached, the predicted vacuum energy density is somewhere between 60 and 120 orders of magnitude larger than what astronomers actually measure when they look at the large-scale behavior of the universe. An order of magnitude is a factor of 10. 60 orders of magnitude is 10 multiplied by itself 60 times. 120 orders of magnitude is 10 multiplied by itself 120 times. The discrepancy between the theoretical prediction and the observed value is, by any measure, the largest mismatch between a theoretical prediction and an experimental result in the history of physics. It is not a small rounding error. It is not a factor of 2, or 10, or 1,000. It is a number so vast that it resists ordinary description. This is called the cosmological constant problem, and it is considered one of the deepest unsolved questions in all of theoretical physics. Something is wrong, or something is missing, and no one yet knows which. One possibility is that the vacuum energy is real and large, but that some unknown mechanism cancels almost all of it, leaving only the tiny residue that observations suggest. What that mechanism might be, no current theory explains. Another possibility is that the calculation itself is missing something fundamental, that quantum field theory, for all its extraordinary precision in other domains, is not yet the right tool for computing the energy of the vacuum at cosmological scales. The honest answer is that this remains open, genuinely, carefully open. What astronomers do observe is that the expansion of the universe is accelerating. Galaxies are moving apart from one another, and the rate at which they do so is increasing over time. Something is pushing space outward. That something is called dark energy. And dark energy may be, as far as current evidence suggests, a manifestation of vacuum energy. The energy of empty space, present everywhere, in every cubic meter of the cosmos, adding up across the vast volume of the observable universe to a pressure that drives its expansion. If that is what dark energy is, then the structure of the vacuum is not merely a local curiosity. It is the engine of the universe's fate. The same ground state that produces the Casimir force between two plates in a laboratory. The same ground state that allows an atom to emit a photon without being touched. That ground state, extended across all of space, may be the reason the universe continues to grow. And yet the numbers do not quite fit. The vacuum energy that theory predicts and the dark energy that observations require are related in form but wildly different in magnitude. The cosmological constant problem sits between them, unresolved, patient in its own way. It does not demand an answer tonight. It asks only to be acknowledged that the vacuum, for all that has been understood about it, still holds something that physics has not yet found the language to say clearly. The ground state of reality, the lowest energy the universe can reach, and still, it is not fully known. Still fluctuating, still, in some deep sense, surprising. And so the vacuum holds its secret quietly. The cosmological constant problem does not announce itself with drama. It simply sits at the center of theoretical physics, patient and unresolved, like a question written in a language that has not yet been fully translated. On one side, quantum field theory, the most precisely tested framework in all of science, predicts a vacuum energy density that is enormous. On the other side, astronomers look out at the universe and measure an accelerating expansion that implies a vacuum energy density that is real, but vastly, almost incomprehensibly smaller than the theory suggests. The two numbers are not slightly off. They differ by somewhere around 120 orders of magnitude. That is not a rounding error. That is not a matter of needing a better instrument or a more careful calculation. It is a disagreement so profound that it suggests something fundamental is missing from the picture. Some principle, some symmetry, some understanding that physics has not yet arrived at. And yet both sides of the problem are well supported. The quantum field theory that predicts enormous vacuum energy is the same theory that describes the Lamb shift, the Casimir force, the spontaneous emission of photons from atoms. It has been tested in dozens of ways and found to be extraordinarily accurate. The astronomical observations that reveal a small but non-zero vacuum energy are equally careful, equally cross-checked. The universe is expanding, and the expansion is accelerating, and something is driving that acceleration. That something is called dark energy. It is not dark in the sense of being hidden or sinister. It is dark in the sense that it does not emit light, does not absorb light, does not interact with matter in any of the ways that ordinary energy does. It is simply a property of space itself, a pressure, a tendency for empty regions to push outward rather than pull inward. And it accounts for roughly 68% of the total energy content of the observable universe. Dark energy may be vacuum energy. That is the simplest possibility, and in some ways, the most striking one. If it is, then the ground state of quantum fields, the irreducible minimum of energy that the universe cannot shed, is not merely a local phenomenon occurring between laboratory plates or inside atomic orbitals. It is spread across every cubic meter of space, across the billions of light years of the observable universe, and its cumulative effect is to push the cosmos apart, slowly but persistently, in a process that will continue for as long as the universe exists. The structure of empty space, driving the fate of everything. There is something quietly extraordinary in that. Not the drama of a collision or an explosion, but the steady, invisible pressure of the ground state, present everywhere, doing its work without announcement. And yet the numbers still do not match. If dark energy is vacuum energy, then the vacuum energy must somehow be almost perfectly canceled, reduced from its theoretically enormous value down to the tiny observed value by some mechanism that leaves only a small remainder. What that mechanism might be, no one yet knows. Some physicists have proposed symmetries that would cancel the vacuum energy exactly, but exact cancellation would mean no dark energy at all, which is also not what is observed. The remainder must be small, but not zero. And explaining why it is precisely as small as it is, without being smaller or larger, remains one of the deepest open questions in theoretical physics. It is the kind of problem that does not yield to a single clever insight. It may require a new framework altogether, something that changes how quantum field theory and gravity are understood to relate to each other. For now, it waits. And while it waits, the vacuum continues to do something else entirely. Something quieter, and in its own way, just as profound. Every particle that exists, every electron, every quark, every neutrino drifting through the dark between galaxies, has a mass, or in some cases, does not. And the reason for that difference, the reason mass exists at all in the form it takes, traces back to the vacuum. The Higgs field permeates all of space. Unlike most fields, which have a value of 0 in their lowest energy state, the Higgs field does not settle to 0, even in the vacuum, even in the ground state, where every other field has quieted as much as it can. The Higgs field maintains a non-zero value. It is present everywhere, at all times, filling space the way a medium fills a container, except that the container here is the universe itself. This is called the vacuum expectation value of the Higgs field. And it is not a small technical detail. It is the reason matter has the properties it does. When a fundamental particle moves through space, it interacts with the Higgs field. The strength of that interaction determines how much the particle resists changes in its motion, which is to say, it determines the particle's mass. An electron interacts with the Higgs field in a particular way, and so it has a particular mass. A top quark interacts much more strongly, and so it is far heavier. A photon does not interact with the Higgs field at all, and so it has no mass and travels always at the speed of light. Without the non-zero vacuum value of the Higgs field, none of this would hold. If the Higgs field were 0 in the vacuum, if it behaved like other fields and settled to nothing in its ground state, then electrons and quarks would be massless. They would travel at the speed of light, unable to bind together, unable to form atoms. The chemistry that builds molecules, the biology that builds cells, the slow accumulation of structure that eventually produces a mind lying quietly in the dark, none of it would be possible. The non-zero vacuum is not a background condition. It is a prerequisite. The Higgs boson, detected at CERN in 2012, is not the field itself. It is a ripple in the field, a small excitation above the vacuum state, a brief disturbance in the medium that fills all of space. When two protons were accelerated to enormous energies and made to collide, the collision briefly disturbed the Higgs field enough to produce one of these ripples. The ripple decayed almost instantly, but its signature was recorded, and it confirmed what the theory had long predicted, that the field is real, that its vacuum value is real, and that the mass of every particle you have ever encountered is a consequence of the ground state of empty space. There is a stillness in that thought. If you let it settle, the vacuum is not empty in the way the word suggests. It is not absence. It is a state, the lowest state, the quietest state, but a state with structure, with energy, with fields that do not vanish, even when everything that can be removed has been removed. And from that structure, from that irreducible ground, the properties of matter emerge. The mass of an electron, the weight of a proton, the reason a hydrogen atom holds together at all of it resting on the vacuum, all of it resting on what remains when nothing else is left. The cosmological constant problem asks why the vacuum energy is as small as it is. The Higgs mechanism asks what the vacuum value of a field can give to the particles that move through it. Both questions point to the same quiet truth, that the ground state of the universe is not a passive stage on which physics performs. It is a participant. It has properties. It has consequences. And those consequences reach from the smallest scales of matter, all the way to the slow, steady expansion of everything. And without that value, without the Higgs field settling into its non-zero ground state, none of what we think of as ordinary matter would exist. Electrons would have no mass. Quarks would have no mass. And without mass, particles cannot bind. They cannot slow down enough to form atoms. They would stream through the universe at the speed of light, never pausing, never gathering, never becoming anything. There would be no hydrogen, no carbon, no slow accumulation of elements in the cores of stars. The universe would be a place of pure, massless motion, light and force, and nothing that holds. It is the vacuum that prevents this. The Higgs field, even in its lowest state, even in what we call the vacuum, carries a value, a non-zero expectation. And it is that quiet, persistent value, not a particle, not an event, just a field resting in its ground state that reaches into the fabric of space and gives mass to the things that move through it. The Higgs boson is something different. It is not the field itself. It is a ripple, an excitation above that ground state. The way a wave is not the ocean, but a disturbance moving through it. When physicists at CERN detected the Higgs boson in 2012, they were not detecting the vacuum value of the field. They were detecting what happens when you strike the field hard enough, when you pour enough energy into a collision that the field briefly shudders above its resting state and produces a particle. That particle decays almost immediately. It lasts for an extraordinarily short time before dissolving back into other particles. But its existence confirmed that the field is real, that the vacuum value is real, that the ground state of the Higgs field is not a theoretical convenience, but a physical fact woven into the structure of space. And yet, the ground state of a field is not always what it appears to be. There is a concept in quantum field theory called a false vacuum, a state that looks stable, a state that behaves, for all practical purposes, as though it is the lowest energy configuration, but is not. Think of a ball resting in a shallow valley on the side of a hill. It is not moving. It has settled. From its own perspective, it is at rest. But below it, further down the slope, there is a deeper valley, a lower energy state it has not yet reached. The ball is stable against small disturbances, a gentle nudge, and it rolls back to where it was. But a large enough perturbation, or in the quantum world, a fluctuation that does not need to be large at all, could push it over the rim and send it tumbling toward the true minimum. This is what physicists mean when they speak of a false vacuum, a state that is locally stable but not globally stable, a state that could, in principle, give way. If the universe is currently resting in a false vacuum state of the Higgs field, then somewhere, at some point in space, at some moment in time, a quantum fluctuation could nucleate a transition. A small region of space could tunnel into the true vacuum, the deeper valley, the genuinely lowest energy state. And from that point, a bubble would form. The bubble would expand, not slowly, not gradually, but at the speed of light, in every direction, carrying with it a different vacuum, a different ground state, different values for the constants that govern how particles interact and how matter holds together. Inside the bubble, the laws of physics as we know them would no longer apply. The masses of particles would be different. The forces between them would be different. The conditions that allow atoms to exist, that allow chemistry to proceed, that allow anything resembling structure to persist, all of it would be altered. The bubble would be invisible until it arrived. There would be no warning, no light preceding it, because nothing travels faster than the boundary itself. This is not a description of something violent in the way we usually imagine catastrophe. It would simply be a change, a quiet, absolute, instantaneous change. From the perspective of anything inside the bubble's path, there would be no perspective at all. And yet, this remains a possibility, not a certainty. Current measurements of the Higgs field, of its mass, of the mass of the top quark, of the parameters that determine the shape of the field's potential, suggest that the universe sits in a region that physicists describe as metastable. Neither clearly stable nor clearly unstable. The calculations place the universe near a boundary, close enough to the stable region that the vacuum might persist for far longer than the current age of the universe, but close enough to the unstable region that the question cannot be dismissed. The uncertainty in these measurements matters. A small shift in the top quark mass, a small shift in the Higgs mass, and the conclusion changes. The universe tips one way or the other, stable or not quite. As of now, the answer is, we do not know with certainty. The data is consistent with metastability. And metastability means the vacuum we inhabit may be the shallow valley, not the deep one. There is something quietly remarkable about sitting with that. Not with fear, the timescales involved. If the vacuum is indeed metastable, are almost certainly vast beyond any meaningful comparison. The universe has existed for roughly 14 billion years, and the expected lifetime of a metastable vacuum of this kind, if it is metastable, is likely many orders of magnitude longer than that. But with a kind of stillness. The ground beneath physics, the vacuum, the lowest state, the thing that remains when everything removable has been removed, is itself uncertain. It may be resting, or it may be waiting, in the way that quantum systems wait, without intention, without urgency, simply in a configuration that has not yet changed. And the Higgs field holds all of this. The mass of every electron in every atom, in every molecule, in every living thing. The stability of the vacuum we inhabit. The question of whether the universe is in its final resting state or merely a long pause before a deeper one. All of it encoded in the ground state of a single field. A field that permeates all of space. A field whose value in the vacuum is not zero. A field that is, in the truest sense, part of what the vacuum is. The vacuum is not a container. It is not the space between things. It is a physical system with a state, with energy, with fields that have values, with fluctuations that have consequences. And those consequences are not small. They reach from the mass of a single electron to the question of whether the universe is stable at all. From the briefest flicker of a virtual particle to the slow expansion of everything. The quantum vacuum is not where physics ends. It is where physics begins. It is the ground from which every particle, every force, every structure in the universe rises, and it is still. Not empty, but still. And yet, even in that stillness, something moves. Not a particle, not a wave, something deeper, something at the very foundation of space itself. There is a scale in physics so small that ordinary language struggles to hold it, a length so brief that it sits at the edge of what the universe can even meaningfully express. It is called the Planck length, and it measures roughly 1.6 times 10 to the minus 35 meters. To place that in some kind of context, a single proton is already almost unimaginably small. The Planck length is to a proton what a proton is to the entire observable universe. It is not merely small, it is the scale at which the very concept of distance may begin to lose its meaning. At this scale, physicists believe that the two great frameworks of modern physics, quantum mechanics and general relativity, can no longer be kept apart. They must meet. And where they meet, something strange is expected to happen to space itself. We tend to think of space-time as smooth, a fabric, as it is often described, continuous and unbroken, curving gently in the presence of mass and energy. And at every scale we have ever measured, it does appear smooth, unruffled, quiet. But the quantum vacuum does not permit true quiet. If vacuum fluctuations ripple through every quantum field, and if space-time itself is subject to quantum mechanics at the deepest level, then space-time, too, should fluctuate. Its geometry should tremble. Its curvature should flicker in and out of definition. This theoretical picture has a name: quantum foam. The physicist John Wheeler first described it in the 1950s. The idea is that at the Planck scale, space-time does not look like a smooth surface at all. It looks more like the surface of the sea in a storm, turbulent, churning, riddled with tiny fluctuations in curvature that appear and dissolve faster than any clock could measure. Topology itself, the basic connectivity of space, might shift and change at this scale. Tiny wormholes threading through geometry, microscopic loops and handles forming and vanishing, a froth of possibility beneath the calm surface we inhabit. It is a remarkable image, and it remains, for now, theoretical. No experiment has yet directly probed the Planck scale. The energies required are so far beyond anything a particle accelerator could achieve that direct observation may never be possible with any technology we can currently conceive. And yet, the universe itself may have left traces. When light travels across vast distances, billions of light years from a distant gamma-ray burst or a faraway galaxy, it carries information about everything it passed through along the way. If space-time is foamy at the Planck scale, that foam might introduce tiny, subtle distortions in the light's path, tiny differences in how photons of different energies travel. Physicists have searched for these imprints in the arrival times of high-energy photons from distant sources. So far, the results have been inconclusive. Some observations place limits on how foamy space-time can be at the Planck scale. Others leave the question open. The universe has not yet answered clearly. But the question itself is one of the deepest we know how to ask: whether the ground beneath all of physics, space-time itself, is smooth or granular, continuous or discrete, a fabric or a foam. And the quantum vacuum sits at the center of that question, because it is the vacuum's fluctuations that would drive the foam, the same restlessness that nudges atoms into emitting light, that pushes two metal plates together across empty space, that gives particles their mass, that may be driving the expansion of the cosmos. That same restlessness, at the very smallest scale, may be quietly reshaping the geometry of space itself. There is something almost meditative in that thought, that beneath the stillness of this room, beneath the stillness of the air, beneath the stillness of the atoms and the walls and the floor and the quiet dark, space itself may be trembling, imperceptibly, constantly, at a scale so small it will perhaps never be seen. And yet physics does not only reach downward into the unobservably small, it also finds ways to work with the vacuum's restlessness directly, to shape it, to use it. There is a state of light called squeezed light. In ordinary light, even in the quietest beam a laser can produce, the quantum vacuum imposes a kind of irreducible noise, a floor of uncertainty that cannot be removed, because the vacuum fluctuates, and light is a disturbance in the electromagnetic field, and the electromagnetic field is never truly still. This noise has two components, two complementary properties of the light field, related to each other the way position and momentum are related in the uncertainty principle. In ordinary light, the uncertainty is distributed roughly equally between them. Neither is more uncertain than the other. But the uncertainty principle does not require equal distribution. It only requires that the product of the two uncertainties remain above a certain minimum, which means it is possible, in principle, to reduce the uncertainty in one property, as long as the uncertainty in the other is allowed to grow. This is squeezed light, a quantum optical state in which the vacuum fluctuations in one chosen property of the light field are pressed down, quieted, made smaller than they would ordinarily be, while the fluctuations in the complementary property rise to compensate. The total uncertainty is conserved. The uncertainty principle is satisfied, but the noise has been redistributed, shaped, squeezed into one dimension and away from another. It is a subtle thing, and it requires careful, precise experimental technique to produce. But it is real, and it is measurable, and it has found a remarkable application. Gravitational wave detectors. When a gravitational wave passes through a detector like LIGO, the Laser Interferometer Gravitational Wave Observatory, it stretches and compresses the arms of the instrument by an almost inconceivably small amount, distances smaller than 1,000th of the width of a proton. At that level of precision, quantum noise is not a minor inconvenience. It is a fundamental obstacle. The vacuum fluctuations in the light used to measure the detector's mirrors introduce uncertainty that can obscure the very signal being sought. Squeezed light offers a way through. By injecting a squeezed vacuum state into the detector, reducing the quantum noise in the property of the light that matters most for the measurement, physicists can push the sensitivity of the instrument beyond what classical physics would permit, beyond what an ordinary laser beam, however powerful, could achieve. LIGO now uses squeezed vacuum states as a routine part of its operation. The quantum vacuum, which introduces noise into the measurement, is also the resource being shaped to reduce that noise. The vacuum is both the problem and the tool. There is something quietly profound in that. The same fluctuations that make perfect silence impossible, that ensure no field can ever be completely still, are also the fluctuations that, when carefully shaped and redirected, allow us to hear the faintest whisper of two black holes colliding 1 billion light years away. The vacuum does not simply impose limits, it offers possibilities. It is a resource, a physical system with structure that can be manipulated, a ground state that is not inert but alive with potential that can be squeezed and shaped and turned toward the most delicate measurements human beings have ever attempted. And all of this from nothing. From the irreducible restlessness of fields that cannot be still. From the uncertainty that sits at the heart of nature. From the ground state of the universe itself. Rest now. Let the vacuum do what it has always done. Fluctuate quietly beneath everything, holding the world in place. There is another way physicists have learned to work with the vacuum. Not by listening for distant collisions, but by looking more carefully at the space inside things, at the geometry of emptiness itself. When you place two mirrors facing each other, very close together, you create a cavity, a small enclosed region of space, and inside that cavity, the vacuum is not quite the same as the vacuum outside it. The walls impose a condition. Only certain wavelengths of light can fit between them. The way only certain notes will resonate inside a hollow instrument. Wavelengths that do not fit are suppressed. They cannot exist there. And so the spectrum of vacuum fluctuations inside the cavity is different from the spectrum outside it. This is the subject of cavity quantum electrodynamics, the study of how confining space changes the nature of the vacuum within it. And the consequences are real and measurable. An atom placed inside such a cavity does not behave the way it would in open space. Its spontaneous emission, the quiet process by which an excited atom releases a photon, depends on the vacuum fluctuations surrounding it. Those fluctuations are what nudge the atom, gently, into releasing its energy. But if the cavity suppresses the vacuum modes that the atom would normally couple to, the atom cannot emit. It remains excited, holding its energy because the vacuum fluctuations that would have initiated emission are simply not there. The cavity has silenced them. And the reverse is also true. If the cavity is shaped so that it enhances the vacuum modes at exactly the frequency the atom wants to emit, the atom emits faster than it would in free space. The vacuum fluctuations are amplified at just the right wavelength, and the atom responds. This is called the Purcell effect, named for Edward Purcell, who described it in 1946. It is a quiet but important demonstration. The vacuum is not a fixed stage on which physics performs. It is part of the performance. Its structure can be altered by the geometry of the space it occupies. And when its structure changes, the behavior of matter changes with it. The vacuum is malleable. That word is worth sitting with for a moment. Malleable. Something that can be shaped. Something that yields to careful arrangement. We tend to think of emptiness as passive, as the absence of things that can be acted upon. But the quantum vacuum responds to its surroundings. It takes on the character of the space it fills. It is sensitive to boundaries, to geometry, to the careful placement of mirrors. It is, in a quiet way, a physical medium. And if it is a medium, it can be engineered. This understanding has moved, in recent decades, from theoretical curiosity to practical technology. Physicists have built devices that do not merely observe the vacuum, but reach into it, manipulate it, use it as a component. Some of the most striking examples involve superconducting circuits. When a metal is cooled to temperatures near absolute zero, not just cold, but extraordinarily cold, within thousandths of a degree of the lowest temperature the universe permits, something changes in it. The electrons inside begin to move without resistance. The material becomes a superconductor, and at those temperatures, the thermal noise that ordinarily masks quantum effects becomes vanishingly small. What remains is the vacuum itself. In laboratories around the world, superconducting circuits are cooled to temperatures measured in millikelvin. A millikelvin is 1,000th of a degree above absolute zero. At those temperatures, the circuits are so quiet that the vacuum fluctuations become the dominant source of activity within them. Not a background hum buried beneath louder noise, but the loudest thing present. And that means they can be studied directly. These circuits contain components called Josephson junctions. A Josephson junction is a thin, insulating barrier placed between two superconductors. Classically, no current should be able to cross it. The barrier is there. The electron should stop. But quantum mechanics does not permit that kind of absolute stillness. The vacuum state carries energy, non-zero, irreducible energy. And that energy allows particles to tunnel through barriers they classically could not cross. The electrons do not go over the barrier. They pass through it, borrowing, in a sense, from the restlessness of the vacuum to do what classical physics would forbid. This is quantum tunneling, and it is not a rare or exotic phenomenon. It is happening constantly, in these circuits, in the nuclei of atoms, in the cores of stars. Nuclear fusion, The process that keeps the sun burning depends on it. Two atomic nuclei, both positively charged, repel each other. Classically, they would need enormous energy to overcome that repulsion and come close enough to fuse. But at the temperatures inside a star, they do not have that much energy. What they have is the quantum vacuum, the non-zero ground state that allows them to tunnel through the barrier rather than over it. Without vacuum fluctuations, without the irreducible energy of the ground state, the tunneling rate would drop. The sun would burn more slowly, or perhaps not at all. The stars themselves are, in part, a consequence of the vacuum's restlessness. But returning to those superconducting circuits, cooled to millikelvin temperatures, humming quietly in their shielded enclosures, they are not merely passive observers of vacuum fluctuations. They are tools for manipulating them. Physicists can use these circuits to generate squeezed states of the vacuum, to probe how fluctuations evolve over time, to test the predictions of quantum field theory in a controlled, tabletop setting rather than in the vast distances of space. They are, in a sense, small laboratories for the vacuum itself. And what these laboratories reveal, again and again, is that the vacuum is structured, it has properties, it responds to what surrounds it, it can be prepared in different states, just as any other physical system can be prepared. The vacuum is not nothing. It never was. It is the ground state of every field that exists, the lowest rung of a ladder that has no bottom, the quietest the universe is permitted to be. And even at that quietest point, it is not quiet. It fluctuates, it polarizes, it shifts the energy levels of atoms, it pushes uncharged plates together, it slows and accelerates the emission of light, it tunnels through barriers, it shapes the geometry of space-time at scales too small to see. It may be driving the expansion of the cosmos. All of this from the ground state, from the irreducible minimum, from the simple fact that nature does not permit perfect stillness. There is something in that worth carrying into sleep, not as a thought to turn over and examine, but as a feeling, a sense of the ground beneath you, not as solid and inert matter, but as fields, resting in their lowest state, fluctuating gently, holding the structure of everything in place through their quiet, ceaseless motion. The chair, the floor, the earth below it, all of it resting on a vacuum that is not empty, a ground state that hums with the minimum energy nature allows. And you, resting too, at your own ground state, breathing slowly, thoughts growing quieter, the boundary between waking and sleep becoming soft. The vacuum fluctuates beneath everything, and everything rests. And somewhere in that rest, something is still moving, not restlessly, not with urgency, but with the quiet persistence that belongs to the vacuum itself. There is a device small enough to hold between two fingers called a Josephson junction. It is, at its simplest, two superconductors separated by a thin layer of insulating material, a barrier, the kind of barrier that, in ordinary experience, stops things. And yet, current flows through it, not because the barrier is broken, not because the electrons find a way around it, but because the vacuum state carries energy, and that energy is enough, just enough, to allow something that classical physics would call impossible: quantum tunneling. The electron does not climb the barrier. It does not go over or around. In a sense that resists easy description, it simply appears on the other side. The barrier was there, and then the particle was through it. The vacuum, with its irreducible ground state energy, makes this possible. This is not a metaphor. It is a measured, repeatable, engineered phenomenon. Josephson junctions are used in some of the most sensitive instruments ever built. Devices that measure magnetic fields so faint they would be invisible to any other technology. Devices that sit at the heart of quantum computers, all of them resting on the fact that the vacuum is not empty, that the ground state hums with just enough energy to let particles pass through walls. And tunneling is not rare. It is not an exotic edge case that physicists discovered in a laboratory and filed away as a curiosity. It is woven into the fabric of the ordinary world. Consider the stars. Every star in the sky, every point of light that has ever guided anyone across water or desert or open field, burns because of nuclear fusion. Two hydrogen nuclei, pressed together by gravity, must come close enough to merge, but they carry the same charge. They repel each other, and the temperatures inside even the hottest stellar cores are not, strictly speaking, high enough to force them together by thermal energy alone. And yet, they fuse. They fuse because the vacuum does not permit a true zero, because the ground state carries energy, because quantum tunneling allows the nuclei to pass through the repulsive barrier that would otherwise keep them apart. Without the non-zero vacuum, without that irreducible hum of ground state energy, the tunneling rate would collapse, the fusion would slow, the stars would dim. All of them. Every sun that has ever warmed a world, every star that has ever collapsed into a neutron star or scattered its elements across a galaxy, all of it sustained, in part, by the fact that the vacuum refuses to be nothing. There is something very still about that thought, something that asks nothing of you, only that you let it settle. The light that reaches you, even the faint light through a window on a clear night, carries in it the record of tunneling, of vacuum energy, of a ground state that would not be zero. Rest with that for a moment. And now, something quieter still. There is a threshold, a theoretical boundary, that physicists call the Schwinger limit. It is the point at which an electric field becomes so intense, so concentrated, that the vacuum itself can no longer hold its shape. At that threshold, the field is strong enough to pull virtual particle pairs apart before they can annihilate, to drag them out of the vacuum and into reality. A particle and its antiparticle, born from nothing but the stress of the field, becoming real, measurable, present. The number is almost too large to feel, roughly 1.3 times 10 to the 18th volts per meter, a field strength that does not exist anywhere on Earth, that has never been produced in any laboratory, that may not exist anywhere in the observable universe except perhaps in the most extreme environments near certain neutron stars. And yet, it is not merely theoretical in the dismissive sense, it is a precise, calculated prediction derived from the same quantum electrodynamics that matches experiment to 1 part in a billion. The Schwinger limit is real in the way that a distant mountain is real. You have not touched it, but you know it is there, and you know roughly how far away it is. What makes it worth holding gently in the mind is what it says about the vacuum. The vacuum has a breaking point, not a flaw, not a weakness, but a threshold beyond which its structure changes, beyond which the boundary between virtual and real dissolves, beyond which empty space begins to produce matter. The vacuum is not passive. It is not simply the absence of things. It has properties. It has a structure that can be stressed and a limit beyond which that structure yields. Physicists are slowly and carefully building toward that limit. Not to reach it, not yet, but to approach it closely enough to see its effects begin to emerge. Extremely intense laser pulses, focused to points smaller than a human cell, carrying more power in a brief flash than entire power stations produce continuously, are being developed and refined with exactly this in mind. The goal is not destruction, it is observation. To watch the vacuum, under sufficient stress, begin to produce real particles from its fluctuations. To see, directly, the thing that the equations have long predicted. No laboratory has achieved this yet. The Schwinger limit remains, for now, beyond reach. But the distance is shrinking, and the experiments are patient. There is something in that patience worth noticing. Physics, at its quietest, is an act of waiting, of building instruments carefully over years, of asking a question and then constructing, piece by piece, the means to hear the answer. The Schwinger limit has been known theoretically since the middle of the 20th century, and the experiments to test it are still being prepared, still being refined, still approaching. Slowly. The way everything approaches its limit, slowly. The way sleep approaches, not all at once, but in gradual degrees. The thoughts becoming less insistent, the body growing heavier, the boundary between here and elsewhere, softening. The vacuum fluctuates beneath all of it. Beneath the Josephson junction, carrying its current through an impossible barrier. Beneath the hydrogen nuclei tunneling toward each other in the core of a distant star. Beneath the laser pulse approaching, increment by increment, the threshold where empty space begins to yield. All of it resting on a ground state that is not zero, that cannot be zero, that carries, in its irreducible minimum, just enough to make the world possible. And you are resting too. Not on nothing, on fields, on a vacuum that hums at its lowest permitted energy, on a ground state that has held the structure of matter in place since the earliest moments of the universe. The barrier between waking and sleep is thin now, and the vacuum, as always, is doing what it does, fluctuating, gently, beneath everything, beneath the weight of the earth, beneath the quiet of the room, beneath the slow rhythm of your breathing. There is no need to hold any of this. Let it go. The ground state will remain, whether you are thinking of it or not. It does not require your attention to continue its work. Rest. And somewhere in that rest, the vacuum continues. Not waiting for anything, not building toward anything. Simply persisting, as it always has, in its lowest permitted state. There is one more thing worth knowing before sleep takes you fully. Something quiet and strange, discovered not in the depths of space, but in a laboratory, in a circuit cooled to nearly nothing. When a mirror moves, not slowly, not gently, but with extraordinary acceleration, pushed to a significant fraction of the speed of light, something happens to the vacuum around it. The virtual photons that ordinarily flicker in and out of existence near its surface find themselves unable to simply vanish again. The motion of the mirror disturbs the vacuum so profoundly that what was virtual becomes real. Photons, actual, measurable photons, are shaken loose from empty space by the movement of a surface through it. This is called the dynamic Casimir effect. And it is, in its quiet way, one of the stranger things the vacuum is known to do. A mirror, moving fast enough, does not merely reflect light. It creates it from nothing, from the ground state itself. The vacuum yields photons to a surface that moves through it with sufficient urgency. No one has yet accelerated a physical mirror to the speeds required. The engineering is, for now, beyond reach. But in 2011, a group of physicists found another way. They built a superconducting circuit, cooled it to temperatures far below anything found naturally in the universe, and used it to simulate the effect of a rapidly moving mirror. Not by moving anything at all, but by changing the electrical properties of the circuit so quickly that, from the vacuum's perspective, the boundary conditions shifted as though a mirror had accelerated through it. And the photons appeared. Real photons, where there had been none, born from the fluctuations of the vacuum, coaxed into existence by a change in geometry rather than a change in position. It was a quiet confirmation, measured carefully, reported without ceremony, that the dynamic Casimir effect is not merely a theoretical curiosity. It is something the vacuum actually does, given the right conditions, given a boundary that moves or changes fast enough. The ground state releases what it holds, and light appears where there was only stillness. Let that settle for a moment. There is another way of thinking about all of this, one that a smaller number of physicists have explored, and that deserves a moment of acknowledgement before it passes. Quantum field theory is the framework that most physicists use to describe the vacuum, and it has earned that trust through decades of precise, confirmed predictions. But there is an older feeling alternative, one that asks whether the vacuum fluctuations might be understood not as quantum phenomena at all, but as something more like a classical field. A real, physical, randomly fluctuating background, present everywhere, not arising from the uncertainty principle, but simply existing as a kind of universal noise. This framework is called stochastic electrodynamics. It treats the zero-point field as a genuine classical entity, a sea of random electromagnetic radiation that fills all of space and cannot be removed. And in this picture, some of the same effects emerge. The Casimir force, certain aspects of the hydrogen spectrum, some features of spontaneous emission, stochastic electrodynamics can reproduce them, at least approximately. Most physicists do not favor this description. The quantum field theory account is more complete, more consistent, more deeply confirmed. But it is worth knowing that the question of what the vacuum fluctuations fundamentally are, whether they are quantum or classical, whether they are a feature of the field or a feature of our description of the field, is not entirely closed. Science holds these questions with patience. And so can you? Now, deeper. There is one more layer to the vacuum, one that lies beneath the electromagnetic picture entirely. The vacuum of quantum electrodynamics, the one that produces the Casimir effect, the Lamb shift, the spontaneous emission of photons, is, in a sense, the simpler vacuum. There is another, the vacuum of quantum chromodynamics, the theory that governs the strong nuclear force, the force that binds quarks together inside protons and neutrons. This vacuum is far more complex. Where the electromagnetic vacuum fluctuates with virtual electron-positron pairs and virtual photons, the QCD vacuum is filled with something denser, more tangled, more difficult to describe. It contains condensates, not fleeting virtual pairs that appear and vanish in an instant, but persistent, stable structures, quark-antiquark pairs that have settled into the vacuum itself, forming a kind of background condensate that permeates all of space. And alongside them, condensates of gluons, the particles that carry the strong force, woven into the fabric of the vacuum in ways that are still not fully understood. This structure is not a perturbation on top of an otherwise empty space. It is the vacuum. The ground state of the strong force is this dense, condensed, fluctuating medium, and everything that exists inside it, every proton, every neutron, every nucleus at the center of every atom, exists within it and is shaped by it. here's something worth holding gently as you drift. A proton has a mass. You might expect that mass to come from the quarks inside it. 3 quarks, each with a small mass, granted by the Higgs field. But the quarks themselves account for only a small fraction of the proton's mass, roughly 1%. The rest, nearly all of it, comes from the energy stored in the QCD vacuum structure. From the gluon fields binding the quarks together, from the condensates of the vacuum itself, from the sheer energy of confinement, of quarks held so tightly that the field between them carries more mass energy than the quarks do. The mass of your body, the mass of the Earth, the mass of every star and stone and grain of dust in the observable universe is, in the largest part, not the mass of particles. It is the energy of the vacuum, stored in the structure of the strong force, locked into the ground state of quantum chromodynamics, present in every proton and neutron that has ever existed. You are not mostly made of matter, in the way that word is usually understood. You are mostly made of vacuum energy, held in a particular shape by a force, acting through a ground state that has maintained this structure since the quarks first condensed in the earliest cooling moments of the universe. And now the facts grow quiet. There is nothing more that needs to be said tonight. The vacuum has been described as best it can be in words which are always a little too slow and a little too solid for what they're trying to carry. The ground state remains beneath the QCD condensate, beneath the Higgs field settled into its expectation value, beneath the electromagnetic fluctuations nudging atoms toward emission, beneath the Casimir plates pressing gently together, beneath the superconducting circuit where photons were born from stillness. Beneath all of it, a minimum, not zero, never zero, but the lowest the universe is permitted to go. And you are there too, in your way. At the lowest energy your body needs to maintain itself, breathing slowly, heart steady, the electrical activity of the mind growing quieter, wave by wave. The vacuum does not sleep, but it does not need to. It simply persists at its ground state, doing what it has always done. And you can let go of the rest. The facts will keep, the vacuum will keep. Rest now. There is one more thing worth holding, gently, before the mind goes fully quiet. Something about where mass comes from. You already know, in a soft way now, that the Higgs field gives particles their mass, that without its settled vacuum value, electrons and quarks would drift through space without weight, without the ability to bind into anything at all. But there is a quieter truth beneath that one. The proton, the particle at the heart of every atom in your body, has a mass, and almost none of it comes from the Higgs. Roughly 99% of a proton's mass comes from somewhere else entirely, from the energy stored inside the structure of the QCD vacuum, from the ceaseless motion of gluons, binding quarks together, from the condensate of quark-antiquark pairs that fills the strong force vacuum like a kind of invisible medium. The quarks themselves are nearly massless. It is the energy of their confinement, the churning of the fields that hold them, that becomes mass through Einstein's quiet equation. So when you rest your hand on your chest and feel its weight, that weight is mostly vacuum energy, made solid, the ground state of the strong force expressed as the substance of you. There is something very still about that. The vacuum has not always looked the way it does now. In the earliest moments of the universe, the cosmos was so hot, so dense, that the vacuum itself was different. The fields that now sit quietly at their lowest values had not yet settled. They were held, briefly, in higher states, states that would not last. As the universe expanded and cooled, it passed through a series of phase transitions, moments when the structure of the vacuum changed, the way water changes when it crosses the threshold into ice. Not gradually, but in a shift, a settling. One of these transitions occurred about a picosecond after the Big Bang, 1/1,000,000th of a second, when the universe was still unimaginably young and unimaginably hot. This was the electroweak phase transition. Before it, the electromagnetic force and the weak nuclear force were unified into a single interaction, and the Higgs field had not yet found its current resting place. It sat above its true ground state in a kind of suspended tension. Then, as the temperature fell below a certain threshold, the Higgs field settled. It dropped into the vacuum value it holds today, and in doing so, it broke the symmetry between those two forces. The electromagnetic and the weak separated particles acquired their masses, and the universe became, in that instant, more like the one we inhabit now. All of that in a trillionth of a second. And the vacuum has held that shape ever since. But there may have been an earlier transition still, one that shaped everything that came after. Some models of the very early universe propose that before the electroweak transition, before even the quarks had condensed, the universe underwent a period of extraordinary expansion, inflation. In these models, the universe was briefly trapped in a false vacuum, a state that appeared stable, that had a kind of local minimum, but was not the true ground state of the field. And because a false vacuum carries energy, vacuum energy, that energy acted like a kind of pressure pushing outward, causing space itself to expand at an exponential rate, doubling and doubling again in fractions of a fraction of a second. The universe grew from something smaller than an atom to something larger than a galaxy, in a time too brief to name in ordinary language. And then the false vacuum decayed. The field tunneled or rolled toward its true minimum, and as it did, the energy it had been holding was released, converted into an enormous flood of particles and radiation, the heat and matter that would eventually become everything. Galaxies, stars, the slow accretion of dust into planets, the long cooling that allowed chemistry, and then life, and then a mind lying quietly in the dark, listening to this. All of it seeded by the moment a vacuum state let go of its energy. There is a way of thinking about the quantum vacuum that treats it as a kind of stage, a neutral background against which physics performs. But that is not quite right. The vacuum is not passive. It has never been passive. It nudges atoms into emitting light they would otherwise hold forever. It presses metal plates together across empty space. It gives the electron its precise energy levels. It shapes the mass of every proton. It may have driven the expansion that set the initial conditions for everything. It is not a backdrop. It is a participant. Perhaps the most fundamental participant there is. Every force, every particle, every structure in the universe exists not against the vacuum, but because of it, woven from its fluctuations, stabilized by its ground state, shaped by the particular values its fields have settled into. The Higgs field, resting at its expectation value, threading through all of space. The QCD condensate, dense with the energy that becomes the mass of matter. The electromagnetic vacuum, alive with virtual pairs that screen and shift and nudge. The cosmological constant, whatever it truly is, pressing the universe outward at a rate that will, over time, carry distant galaxies beyond the reach of any signal. All of this is the vacuum, expressing itself, and you are made of it. Not metaphorically, literally. The atoms in your body are mostly empty space. And that space is not nothing. It is the quantum vacuum, held inside the boundaries of electron orbitals, shaped by the fields that give those orbitals their structure. The mass you carry is mostly the energy of the QCD vacuum, bound into protons and neutrons by the strong force. The light that your cells use, the photons released by molecular transitions, each one initiated by a fluctuation in the electromagnetic ground state. You are a local structure in the vacuum, a region where the fields have organized themselves, temporarily, into something that breathes. The breath is slower now. The thoughts are softer. There is no need to hold any of this carefully. The facts will remain whether or not the mind keeps them tonight. The vacuum will remain. It has no need of memory. It simply is, at every point in space, at every moment, doing what it has always done. Fluctuating, persisting, holding the ground state, the lowest energy the universe is permitted to reach, and yet not zero, never zero, always that irreducible minimum, that hum beneath everything. You are resting near your own ground state now. The body has slowed. The electrical patterns in the mind are growing long and gentle. The boundary between thought and sleep is becoming soft. Let the vacuum hold what it holds. Let the fields rest at their values. Let the proton carry its mass without your attention. Let the Higgs field sit quietly where it settled, a picosecond after everything began. You do not need to understand it tonight. You only needed to hear it, to let the shape of it pass through you, the way a very slow wave passes through deep water, barely disturbing the surface, and then gone. Rest now. The ground state remains, and somewhere in that stillness, something else is present. Not the vacuum. Exactly. Something woven through it. Something that does not glow, does not emit, does not reflect a single photon of light. And yet, as far as we can tell, outweighs all the visible matter in the universe by roughly 5-1. It is called dark matter. And the evidence for it is quiet and patient and very difficult to dismiss. It begins with rotation. When astronomers measure how fast stars orbit the center of a galaxy, they expect a particular pattern. The stars near the outer edges, far from the dense, luminous core, should move more slowly, the way the outer planets of our solar system move more slowly than the inner ones. Gravity weakens with distance. That is the expectation. But that is not what they find. The outer stars move just as fast as the inner ones, sometimes faster than they should. The rotation curves, the graphs that plot orbital speed against distance from the center, stay flat or even rise, where they should fall away. This was measured carefully by Vera Rubin and her colleagues in the 1970s across dozens of galaxies. The pattern held everywhere they looked. The stars at the edges were moving too fast to be held by the gravity of the visible matter alone. Something else had to be there. Something massive, spread through and around the galaxy in a vast, diffuse halo, invisible, but gravitationally present. The flat rotation curve is still one of the clearest signals we have, and it is not the only one. Light bends around mass. Einstein's general relativity tells us this, and it has been confirmed many times. When a very massive object sits between us and something more distant, the gravity of that object curves the path of the light, distorting and sometimes multiplying the image of whatever lies behind it. This is called gravitational lensing. And when astronomers measure how much lensing a galaxy cluster produces, they find that the bending is far stronger than the visible mass could account for. The cluster is deflecting light as though it contains far more matter than the stars and gas we can see. The extra mass is not glowing. It is not emitting X-rays. It is simply there, bending space around it, making its presence known only through geometry. There is a particular observation that many physicists find especially compelling. Two galaxy clusters that collided long ago. The light and gas of each cluster slowed and separated during the collision, as gas clouds do when they pass through each other. But the gravitational mass, as measured by lensing, did not slow. It passed through, largely unaffected, as though whatever carries most of the mass barely interacts with anything at all. The mass and the light came apart. That separation is hard to explain without something that does not interact through electromagnetism, something that does not collide, does not heat up, does not radiate, something that only makes itself known through gravity. And then there is the large-scale structure of the universe itself. The galaxies are not scattered randomly. They form filaments and sheets and vast empty voids, a cosmic web, delicate and enormous. The simulations that reproduce this structure most accurately are the ones that include large amounts of cold, slow-moving, non-luminous matter present from very early times. Without it, the web does not form correctly. The galaxies do not cluster the way they do. The structure we observe requires something that began clumping under its own gravity long before ordinary matter could, seeding the scaffolding that everything else eventually fell into. These three lines of evidence, rotation curves, gravitational lensing, structure formation, each arrived through different methods, different instruments, different teams, and they all point in the same direction. Something is there. The question is what? The leading candidates have changed over the decades. For a long time, physicists hoped the answer might be a class of particles called WIMPs, weakly interacting massive particles. They would have mass, they would feel gravity, but they would pass through ordinary matter almost without effect, interacting only through the weak nuclear force. They were theoretically appealing. They arose naturally from extensions of the standard model of particle physics, and their predicted abundance matched, roughly, what cosmology required. Experiments were built deep underground, shielded from cosmic rays, filled with ultra-pure materials, xenon, germanium, argon, waiting for the rare moment when a dark matter particle might nudge an atomic nucleus just enough to leave a trace of heat or light. They have been waiting for a long time. The detectors have grown more sensitive with each generation. The volumes of target material have increased. The backgrounds have been reduced to extraordinary levels, and the signal has not come. Not definitively. Not yet. This does not mean dark matter is not there. It may mean WIMPs interact even more weakly than expected. It may mean the mass is different from what was assumed. It may mean the answer lies elsewhere entirely. Other candidates remain. Axions are among them, very light particles, originally proposed to solve a different problem in particle physics, but which could also account for dark matter if they exist in sufficient numbers. Experiments are searching for them now, using strong magnetic fields to coax axions into converting into detectable photons. The signal, if it exists, would be extraordinarily faint. Sterile neutrinos are another possibility. Ordinary neutrinos barely interact with matter, passing through the Earth as though it were not there. A sterile neutrino would interact even less, only through gravity. It would be nearly impossible to detect directly, but it might leave subtle imprints in the X-ray emissions of galaxy clusters. And some researchers believe they have seen hints of exactly that. The hints remain contested. There are those who ask whether the problem might instead lie with our theory of gravity, whether modifying the equations of general relativity at large scales might explain the rotation curves without invoking unseen matter. Some modifications do reproduce certain observations, but they struggle with others. The colliding clusters, in particular, are difficult to explain without actual additional mass. Most physicists remain unconvinced that gravity alone is the answer. And so the search continues. Underground detectors listening for a whisper of recoil. Radio telescopes scanning for axion signals. Space observatories mapping the distribution of mass through lensing across billions of light years. Particle colliders looking for signatures of new physics that might point toward what dark matter is made of. None of it has yet produced a confirmed detection. And there is something quietly remarkable about that. The universe is, by mass, mostly something we have never touched, never seen, never caught in any instrument. It shapes every galaxy. It determined the architecture of the cosmos. It is present in the space around you right now, passing through the walls, through the floor, through you, if it is what we think it is, without leaving any trace you could feel. The visible world, the world of light and matter, and everything you have ever seen or held, is a minority. A thin, luminous layer over something vast and dark and patient. And the dark does not announce itself. It does not need to. It simply curves space around it, holds galaxies together, and waits the way deep things wait, without urgency, without sound. You are drifting now. The mind is releasing its hold on the details. The rotation curves are fading. The lensing maps are dissolving. What remains is only the shape of the idea that the universe contains more than it shows, that the darkness is not empty, that something immense and quiet is woven through everything. Let that settle. You do not need to name it tonight. You only needed to hear that it is there. The body is still. The breath is slow. The dark matter passes through, as it always has, as it always will. Indifferent, invisible, and present. Rest now. And beneath all of that stillness, there is something stranger still. Not dark matter, which holds galaxies together from the outside, but something woven into the fabric of space itself. Something that lives in what we call the vacuum, and what we call nothing. You might think of a vacuum as absence, a room with everything removed, silence after the last sound fades. But quantum physics looks at that emptiness and finds it is not empty at all. Every field that exists, the electromagnetic field, the fields that carry the nuclear forces, the field that gives particles their mass, each one of them has a lowest possible energy state, a ground floor, so to speak. And the strange thing, the thing that took physicists a long time to accept, is that this ground floor is not zero. It is never zero. There is always something there, a kind of irreducible hum built into the structure of reality itself. This is called zero-point energy. And it exists because of a constraint so fundamental it cannot be worked around. The uncertainty principle. A field cannot simultaneously hold a precise value and change at a precise rate. It cannot be pinned down completely. So it moves. It fluctuates. Even at absolute zero temperature, even in the coldest, most isolated corner of space imaginable, the fields keep moving. These are not imperfections in the theory. They are not noise to be subtracted away. They are what the theory predicts. They are what the vacuum is. The quantum vacuum is the lowest energy state the universe can occupy, and yet it is not a state of rest. Pairs of particles flicker into existence and vanish again, too briefly to be caught directly. A particle and its antiparticle borrowing energy from the vacuum for a moment so short it leaves no lasting trace. We call them virtual particles, and we cannot observe them directly, but we can observe what they do to the things around them. In 1948, A Dutch physicist named Casimir made a quiet prediction. If you place two uncharged metal plates very close together in a vacuum, he said a force would push them toward each other, not because of any charge, not because of any magnet, but because of the vacuum itself. Between the plates, only certain wavelengths of vacuum fluctuation can fit. Outside the plates, all wavelengths are present, and so there is more vacuum activity outside than between them, a gentle, inward pressure from the surrounding emptiness. The plates are pushed together by nothing, by the shape of nothing. This was confirmed experimentally in 1997. The measured force matched the prediction to within about 1%. A year before Casimir made his prediction, a physicist named Willis Lamb was measuring the energy levels of hydrogen with great precision. He found a tiny discrepancy, a small shift in two energy levels that should, according to the theory of the time, have been identical. This became known as the Lamb shift, and it earned him a share of the Nobel Prize. The shift exists because vacuum fluctuations interact with the electron inside the atom, nudging its energy ever so slightly. The vacuum leaves its fingerprint on the simplest atom in the universe. These measurements, the Casimir force, the Lamb shift, are part of why physicists trust quantum electrodynamics so deeply. QED, as it is called, describes how light and matter interact through the medium of the vacuum. Its predictions match experiment to roughly 1 part in a billion. It is the most precisely tested theory in all of science. And all of it rests on the reality of an active, fluctuating vacuum. There is something almost tender about what this means for light. When an excited atom releases a photon, when it glows, it does not do so because something external strikes it. It does so because the vacuum nudges it. The fluctuations provide a tiny perturbation, a whisper, and the atom responds. Without the quantum vacuum, excited atoms would theoretically hold their energy forever, never releasing it, never shining. The light in the universe exists, in part because empty space is never truly still. Further out, at the edges of what we can currently test, the vacuum becomes stranger still. An observer accelerating through the vacuum would perceive it differently from one standing still. The accelerating observer would feel a faint warmth, a thermal bath of particles, where the stationary observer sees nothing at all. Both descriptions are correct within their own frames of reference. This is called the Unruh effect, and it has not yet been directly measured, but it follows from the same mathematics that describes everything else we have confirmed. Near a black hole, something related occurs. Vacuum fluctuations near the event horizon can be separated, half of a virtual pair falling inward, the other escaping outward as real radiation. The black hole slowly loses mass this way, over timescales almost beyond imagining. The vacuum, even there, is not passive. And then there is the largest question of all. The energy of the vacuum, summed across all of space, should, according to quantum field theory, be enormous, staggeringly large. But when astronomers measure the actual energy density of empty space, the number they find is incomparably smaller. The theory and the observation disagree by a factor so vast it is difficult to even write down. This is called the cosmological constant problem, and it remains one of the deepest unsolved questions in physics. What astronomers do observe is that the expansion of the universe is accelerating. Something is pushing space apart. We call it dark energy, and it may be the energy of the vacuum itself, the ground state hum of all the fields, expressed at cosmic scale. If that is what it is, then the structure of empty space is directly shaping the fate of everything. The Higgs field is part of this story too. It fills all of space, and in the vacuum, it does not rest at zero. It holds a value, a kind of permanent presence, and it is this presence that gives electrons and quarks their mass. Without it, Atoms could not form. Without it, you could not form. The Higgs boson, detected quietly in 2012, is simply a ripple above this ever-present vacuum state. There is a possibility, held lightly, not with alarm, that the vacuum we inhabit is not the lowest possible state, that it is metastable, resting in a valley that is not the deepest valley. A quantum fluctuation, somewhere in space, could in principle begin a transition to a lower state, a bubble expanding at the speed of light, carrying different physics inside it. Current measurements suggest the universe sits near the edge of stability, neither clearly safe nor clearly not. Most physicists do not lose sleep over this. The timescales involved are longer than the current age of the universe, many times over. And at the very smallest scales, smaller than any instrument has yet reached, the vacuum may not even be smooth. Space-time itself, at the Planck length, may dissolve into something turbulent and foaming, geometry flickering. The fabric of space, not a fabric at all, but something more like a froth. We do not know, not yet. What we do know is this: the vacuum is not a backdrop. It is not the absence of physics. It is physics, active, structured, measurable, and strange. The space inside this room is full of it. The fields are here, fluctuating. The virtual pairs appearing and vanishing in intervals too brief to name. The Higgs field holding its quiet value, giving everything its weight. You are resting inside the lowest energy state of the universe. And it is not still. But you are. The breath slows. The fields continue their ancient, silent work. And you drift